Hello and welcome to today's webinar. My name is Abdullah Ibrahim. Today we'll be looking at the new features and enhancements which came as part of the Tekla Structural Designer 2020 Service Pack 4 update. So the three main areas which we'll be looking at today are all considered as modelling enhancements. These are ancillary loads, inactive members and shear only walls. So with ancillary loading, this is a new feature released as part of the Tekla Structural Designer Service Pack 4 updates. This feature allows you to create loading for ancillary items such as ladders with and without cages, stairs, pipework, walkways, etc. These loads can either be set as line or area loads. We'll now look at how to model these in Tekla Structural Designer. Here we have a simple reinforced concrete model. In this model, we will be modelling two flights of concrete stairs starting from the beam at the base, which is this beam here, to the beam at the first floor landing. We'll then repeat the process between the first floor and second floor to model a second flight of stairs. We need to understand the load that we're going to be applying before applying it. To see these, we need to go into the model settings, which is found under the home ribbon. In this window, if we expand the loading tree, we'll see there are options for both line and ancillary loading types. In this window is where the loads for each ancillary type can be set. We can see that for concrete flights, the program will apply a dead load of 4.5 kilonewtons per square meter and an area imposed load of 4.8 kilonewtons per square meter. These values can be changed to suit your desired values. If we come out of this window now, the ancillary loads can be applied by clicking on any of the ancillary loading icons, which are both found under the model ribbon over here. I will be selecting first the area ancillary load type. And once we select this option, the yellow bar will appear at the top of the scene view, giving you a hint as to show you how those loads can be applied. Before we go to apply any of the loads, what we must first do is review the properties, which are all found over here in the properties window. Now, the type of load over here is shown as a walkway or a catwalk. What I'm going to do first is change this load, or change this load type, by clicking on this drop down and selecting concrete stair flight, landing. In this first example, we're not going to be applying a landing. What we can now do once we've set the type is we can now review the remaining properties to ensure that all our properties for this load type are correct before we apply any of the load. The first thing we'll review is whether the default values are acceptable. In this case, I'm just going to accept the default values. If you are not happy with the default values in isolated situations, what you can do is you can just simply untick this box over here and you can manually define the dead and imposed loads. I'm going to apply a guardrail height of 1 meter. And in this example, there will be no landing, so the top and bottom landing values are both going to be 0 meters. We will now define the geometry of the ancillary load. To do this, we just simply click the corner points where we're going to be modelling those ancillary loads, which are the 2 points at the extreme ends of the beam at the base. And I'm just going to snap these onto the intersections over here. I'm just going to double click on the final point to complete the insertion of this ancillary load. Just going to double right click to escape that. It's important to understand that when we came to set the properties, the rotation value I kept as 0 degrees. And if I'm just to rotate the model around a little bit, we can see that the way that the loads are being decomposed is they're decomposed from the beam at the base to the landing beam at the first floor level. What we'll now do is we'll now look at the load cases window. which is found under the load ribbon, load cases. And what ancillary loading does is we've already, before applying the ancillary load, we reviewed the loads that aren't going to be modelled as part of the ancillary loads. What the program does is whenever any ancillary load or any type of ancillary load has been created, it automatically creates load cases and sets the load types accordingly. There are other things that can be done for each load case. So when you work into Eurocodes, what you can do is you can also set the psi factors for each load case just simply by selecting the load case and going into the combination factors and making those changes there if you feel they're necessary. What we'll now do is we'll now look at the decomposition of the load. To do that, under the load ribbon, I'm just going to perform a decomposition first. And once a decomposition has been performed, I'm going to select one of the load cases and we can see the profile of the load or the decomposed load. If you wish to see the magnitude of the loads, you can just simply go into scene content, expand loading, and under decomposed, you can turn on text. And this turns on the values for the decomposed loads. You can also turn on text for the area ancillary too. I'm now going to insert the second set of concrete stairs. This time, the stairs are going to include a 2-meter landing. I'm going to create 2 sets. So if you have a look at the profile of the load that we've applied over here, it's going to be applying one set over here just to cover the remaining width and another set over here. To do that, again, I'm going to go into the model ribbon, select area ancillaries, select the concrete stair flight again, set the guardrail height as 1 meter again, but this time I'm going to set a top landing height of 2 meters. Sorry, top landing length of 2 meters. I'm then going to insert them like this. So that's 1 and that's 2. It's important to understand that with the ancillary loading, if you've modelled a stair with landings, that each one of these are going to be created as a separate ancillary load. So if you hover over that, we can see that in the select entities window is giving us a set of ancillary loads. In this case, AA2 flights with landings. Over this load over here specifically is AA3, and this lower load over here for the stair is AA2. If I perform the decomposition again, and why I mentioned that these are both, or these loads are created as 2 separate ancillary loads, is if I were to go into ancillary dead, we can see that there are 2 decomposed loads there on the top beam. So one of those loads is the decomposed loads from the landing and the other is the decomposed loads from the stairs. Over here we have a model which is similar to the model that we looked at before. So there's a small difference with this beam here just moved out a little bit further. Not really a big difference. The main difference in the model is that the beams on the first floor and second floor have been removed. I'm using this example to show how ancillary loads can be decomposed onto flat slabs. Now there is a little bit of a limitation with this, and I'll show you what the limitation is and how to work around it as well. If we go to Home and Model Settings and review the area ancillary loading properties again for the concrete stairs, we can see that the loading is the same as what it was for the previous example. Also, if I go into the Load ribbon and open the Load Cases window, we can see that there are no ancillary load cases in the window or listed. If I now go into the Model ribbon and create an area ancillary load again, and choose the concrete stair flight and landing, and just set the same properties as I had before. So just a guardrail height of 1 meter for the first flight. And now 2 meter top landing for the second flight. If I now go to perform a decomposition, again, and turn on one of the ancillary load cases, I'm just going to turn on the text for decomposed loads as well. We can see how the loads have been decomposed. So previously, where they were decomposing onto a beam, we could see that we just got a single line load on the beams where the ancillary loads were coming onto, and where it had a landing as well, you saw that there were 2 loads. So here we still see that there are 2 loads. However, because they're decomposing onto a flat slab, you do see the effect that this has on all 4 edges of that flat slab. The beam over here at the bottom, it's decomposing there normally, just a single decomposed line load there. If you have a look at the first floor level, this is the limitation that I was referring to. On the first floor level, as we didn't have a beam, if you then have a look at the loads that have been decomposed on there, no loads have been decomposed, and the only way around that is to simply put in some kind of beam element. I'm just going to put a concrete beam in just to demonstrate this. If I then go into load and decomposition again, we can see that the decomposition has now been performed at the first floor level with the beam in place. You could equally use a beam of any other kind by simply changing the material, or you can also change the characteristic to use an analysis element instead. Perform the decomposition again, and you can see it's the same decomposition that takes place. So here I've just shown that ancillary loads can be decomposed onto the edges of flat slabs, not onto flat slabs, with a slight limitation. So I have now shown how ancillary loads can be modelled on an inclined plane, and also how they can decompose onto beams and flat slabs. Importantly, the type of ancillary loads I've only used so far have all been area loads. I will now show that the same loads can be modelled using line ancillary loads instead, and I'll also be showing the different planes that the ancillary loads can also be applied in. So in this example, what I will do is I will replace this flight of stairs here with a line ancillary load instead. To do that, I'm just going to delete this load and run the decomposition again. So importantly, running the decomposition again to show that the load is no longer applied. I'm going to go into the model ribbon and this time select line ancillary. So similarly to working with area ancillary loads, it does give you a hint over here as to how to model the load. You do have properties in the properties window that will allow you to also define how these ancillary loads are modelled. You've got a continuous box over here. Now, the continuous box just means that once you've inserted the first ancillary load, if you'd want to insert a second immediately, I'm going to untick this box now, because in this case we only just want to have a single flight of stairs spanning from this beam onto the first floor beam. Importantly also with line ancillary loads is you define the centre of where the ancillary load is, and when you're modelling and in the properties window you define the width. So I'm just going to define the width here as being 2 meters, as that is how wide this beam is over here and how wide the space is at the first floor landing. Again, we'll also set the type, make sure the type is set correctly, as this is where the load values are pulled from. We'll also set the geometric properties in the properties window as well. And the way I'm going to model this load now is to follow the hint, which tells me here to pick point 1. Point 1 being the center or the midpoint of this beam. I'm going to click once here, and now it's giving me a hint to pick point 2. Point 2 being the midpoint of this beam here. Once I pick this point over here, it then gives me an option to pick the reference plane, and the reference plane, I want them to be in the plane of this inclined plane, so I'm just going to pick any point on that inclined plane, and that completes the modelling of that load. I'm going to perform a decomposition again, and when I perform a decomposition, this time the load is just decomposed as a single point load on the beam at both ends. So there are no real differences between modelling area loads and line ancillary loads. The only difference is really, instead of defining the width when you're inserting the load, what you do for a line load is you'd pick the centre of where the middle of the load will be when you're picking the points, and the width is defined in the properties window. I'm going to show how an ancillary load can also be modelled vertically. So I'm going to be modelling 2 vertical loads here. The first being a ladder without a cage, and the second flight being a ladder with a cage. Once again, to do that I need to go into the model ribbon, select the line ancillary, and I'm just going to make the ladder 1.5 meters wide, and I don't want it to be continuous. So what I'm firstly going to do is pick the ladder without cage first, set the width as 1.5, and make sure the continuous box is not ticked. If I now go to model the ladder, I'll just simply pick the first point, pick the second point, and then just pick any point on that plane to define the load. And I'm going to repeat the process this time, but this time with a cage, and I'm going to do that one again. Oops. Now, I'm going to perform a decomposition. And if we go into the status window, we'll see that a decomposition of the load at that point has been performed at the bottom of the first, the top of the lowermost ancillary load, and the same applies above. The only issue with this is, while it's applying an ancillary load, it's decomposing that load onto nothing. So what you will need to do is you will need to have some sort of member over here that can take that load, ideally a beam at the base. We can see that not having a member at the bottom, where this point load over here can be decomposed to, may present an issue. If I were to perform a validation, I can see that when looking under the validation tree, it tells me that under ancillary dead, that there's an issue showing that one of the loads cannot be decomposed. It's only referencing ancillary dead over here. And the reason for that is if I go into Home, Model Settings, and have a look at ladders with or without cages, we can see that for ladders, the imposed loads are 0. So applying a line load of 0 kilonewtons in the imposed load will not flag up any issues with any of the ancillary imposed loads. If I were to perform an analysis for the ancillary dead and the ancillary imposed load cases, and review the loading summary, so under the loading ribbon, under the loading window in the project workspace, and review ancillary dead, we can see that the total reaction does not equal the decomposable loads. So to resolve that issue, what we need to have is we need to have some kind of member over here again at the bottom to take that load. If I go into model, I'm just going to model a member that can take that ancillary load. Just model the steel beam. Again, it can be any beam item or even an analysis element. If I run that, we can see that now that ancillary load has been decomposed onto this beam over here. And when we have a look at the ancillary dead, we can see that the total load on structure and total reaction now balances. So here what I've shown is how to model a vertical ancillary load. And I'm also going to be modeling a walkway across the top over here. I'm going to do that using a line ancillary. So if I click on the line ancillary item, this time select walkway or catwalk. I'm going to keep continuous ticked. I'm going to set the width as being 2 meters. And this time I'm just going to model a walkway starting from this beam here, decomposing onto this point here, and a second walkway like so. If I click escape there, or press escape, we can see that we've modeled the 2 walkways. If I then go on to decomposition, we can see how that decomposition is performed. So we've modeled 2 walkways, essentially just a single walkway at the very top, where the ancillary loading at first is spanning onto the beam at the end, and it's being decomposed onto both beams at the landing side as well. The ancillary loads for this walkway can even be modelled as a single load. I'm just going to delete this ancillary load over here. Can even be modelled as a single load. I'm just going to untick the continuous box, spanning from the beams at the extreme ends. And when we're modelling an ancillary load within a horizontal plane, it doesn't ask us to define the plane using the third click. If I perform a decomposition, the loads are now decomposed onto the extreme, the beams at either end. So no load is decomposed onto the beam at the landing in this case. So it's just a little bit of caution when modelling horizontally or any sort of ancillary loads that will be continuous. If they are going to be continuous, make sure you do pick this point if you are wanting it to decompose onto that point as well. So the last thing I'm going to show with regards to ancillary load is decomposition of loads that don't end either at the edge of a slab or on a beam. So far, all of the loads that we've had decomposed have either met the edge of a slab or have been supported by a beam or an analysis element like we have over here. What I'm going to do is I'm just going to model a walkway at the top, similar to what we did in the previous example. However, it's going to end at this intersection over here. I'm going to remove these 2 ancillary loads, and the only reason I'm doing it is just to make the decomposed loads clearer when viewing. So it's just simply to declutter the view over here. I'm going to model a line ancillary load, model that 2 meters wide, just keeping the default values. I'm going to start the load over here and end the load at this intersection over here instead. If I go into run the decomposition, we can now see how that load is decomposed. So the load, the width and the line load itself is the same as it was before. However, the length is slightly shorter, hence why the magnitude is less. And if you have a look at how the loads are decomposed, the loads are decomposed as a single point load within the middle of a slab where the ancillary load ends, and you can see how that load is decomposed in turn onto the members supporting this flat slab here. So here are the key points to show with regards to the ancillary loads that we just looked at. So everything listed on this slide I've demonstrated. I've demonstrated that how line and area ancillary loads, dead and live load values must be set in model settings. How ancillary loads do create their own load cases. Line ancillary loads are decomposed at point loads at the ends, and area ancillary loads are decomposed as line loads or UDLs. All ancillary load tools can be found within the model ribbon, and they're shown in the screenshots in this slide. So another one of the new features that were released as part of the 2020 Service Pack 5 update is the option to now model inactive members. In previous versions of the program, you always had the option to make analysis elements or elements inactive. As part of this update, you can now make single spanning beams, braces, purlins and rails inactive as well. So the benefit of this will allow you to have loads decomposing onto members without those members being active within the analysis. Also, inactive members can be used in conjunction with ancillary loads. So here is a model that consists of members, which we don't really wish to see the analysis results for. We only want those members to decompose the loads onto the mainframe and so on. If we right click on a member and open the properties of that member, in fact equally we can double click on this member, what we can see is for the different member characteristics, some of these member characteristics have this active box included over here. So those members include beams. That's not available for columns, but it's available for things like purlins, rails, and even analysis elements. I'm just going to keep this member active for now. You can also find the properties, this same property in the properties window over here under the active box, which the active box is ticked. Now, when the member's active, I'm just going to run the analysis over here. And if we go to review the analysis results, say for that combination, if I turn on the deflected shape, we can see the deflected shape is shown for these members, which we're only really wanting to use as decomposition elements. If I were to select all of the purlins, tick the inactive box, and the cold rolled members, which in this case are all acting as eaves beams, if I were to make those inactive as well, and rerun the analysis, we can see that when it comes to actually running the analysis and viewing the deflections, it just makes the deflections much easier to see. So rather than cluttering the view with the analysis of these elements now only act as load decomposition tools. So the loads from these that are being decomposed on these elements will still in turn be decomposed onto the main framing members. So now what I will do is I will show how inactive members can now work with ancillary loads. If we go back to this model over here, so this is the first example we looked at, and we review the decomposed loads. So the loads are decomposed in the same way as they were before. I'm just going to run the analysis, and the reason I'm running the analysis is just to show the loading summary, to show that over here the total load applied is equal to the total reaction, or the total load on structure is equal to the total reaction for both of the ancillary load cases. If we turn on the vertical support reactions, we can see what the values of those support reactions are. And we can see that over here it's 9.5, and the reason it's 9.5 is because we have, on each support, is because we have a 2 meter beam decomposing a 9.5 kilonewton per meter line load. If we click over here and make this member inactive and perform the decomposition again, we can see that the decomposition is the same. So it's still decomposing onto this member, which, if I were to just look at the solver model that we're currently working to, we can see that that member there does exist. However, it's modeled using a dotted line in the solver model, meaning that that member is no longer active. If I were to run the analysis again for the same two load cases, we can see that we get the same reaction even though this member here is inactive. So the loads are being decomposed onto the inactive members, which in turn are taking the loads through to the supporting members or the supports. If we have a look at the dead load again, or the ancillary dead load in the loading summary, we can see that we have the same load that we had applied before and the same reaction. Now this can be done for other beams in the model as well. You can also make those inactive and review the decomposition, which again does not change. Rerun the analysis and we can see that the same reaction is given. I'm now just going to look at another model this time. So this is the same model that we had before. So looking back at this flat slab example where we'd modelled a dummy analysis element, the dummy analysis element is there to simply decompose the loads because of the limitation with regards to having two flat slabs. If I were to run the analysis for the ancillary dead and imposed load cases, we can see that if we have a look at the solver, it's just flagging up an issue over here with regards to the ancillary dead plus imposed, and the reason for that over here is just simply this element is weak with its default properties. However, its default properties are going to be irrelevant when we make this element here inactive and run the analysis again. We can see that we no longer have the large deflection, and what you might also see is the loading summary not tallying up when you have an analysis element. In this case, because we made the analysis element inactive, all the analysis element is doing is simply putting the load from the ancillary loads that it's taking onto the members that this element here is supported by. Again, we can do the same thing by making this element over here inactive, and what that results in, all of the load, what we can see now in the loading summary is all of the load that's been applied onto the model is still applied onto the model and has successfully found its way to the support, even via the inactive elements. Now, the final thing I'd like to mention with regards to inactive members, is that the inactive members can now be seen graphically as well. To do this, the easiest way would be to go into the review view. So you can either right-click on the tab at the top and select the review view icon option, or you can pick the icon over here at the bottom right-hand corner of the screen. If you click on the Show Alter State icon within the review ribbon, under Attribute, you have this active box over here, which will then show you all of the active and inactive items. So all of the items that can be made inactive are shown in green, and to simply inactivate an item, you can just simply click on an item to toggle it as being inactive, as shown by the yellow, or click on it again to make them active. If you want to set every member as being inactive, or every member that can be inactive to be inactive, you can just simply change the mode from toggle to set inactive and just window around the entire model. Therefore, every single spanning member, brace, every single span beam, brace, rail or purlin will be set as inactive. If you want to set those again as being active, you can just simply select the set active, and you can also filter further by changing the entity type to look at beams only. So now this is only looking at beams, and if you want to make just the floor beams active, you can just simply window around the floor beams carefully in this case to not include the eaves beams and make all those members active again. So the final subject under modelling today is shear only walls. So these are walls that are used to only resist lateral forces in the plane of the walls. The most useful time you would use these are for panels that are there to resist only lateral forces, such as infill panels or infill masonry panels, as an example. It's important to understand how the solver models behave. Understanding how the solver models behave will give you a better understanding of how the output is attained. And I would advise that before using these two, definitely have a look at the release notes to find more information on how the solver models are created and also where these would be useful. So the product guide here provides some background. Scrolling down, it provides a background on the different failure types. So here there's an example of sliding of the bed joints, cracking, or compression in the corner due to rocking or toe compression failure, as it's stated on the website. Scrolling further down, there's some more theory provided. And scrolling all the way to the bottom, there is an explanation over here showing how the solver models are created for the different kind of panels. So you're looking at upper panels at the top and panels at the base, showing you where the solver element's taken and how the forces are decomposed onto the corner nodes. So I'm now going to show how these panels are modelled. I'm firstly just going to create a simple rectangular grid, just one bay in both the X and Y direction. So just out of interest, if you want to see the geometry, it's one bay of 6 in the X direction and one bay of 4 in the Y direction. So to create a regular meshed shear wall, the way you do that is under the model ribbon, under meshed wall. You've also got the option of a mid-pier wall as well. If you click on meshed wall and you review the properties, what you can do is you can then just simply insert a meshed wall like so. And if you want to insert a shear only wall, you would do that by selecting the wall type drop down and selecting the shear only wall option. That there's modelled a shear only wall. If I have a look at the 3D view, we can see how the walls will appear differently. So what you have over here is you have, for the meshed wall, is you just have line supports where at the bottoms of each one of the FE nodes, you will see that you'll have a support element created there. Whereas for a shear only wall, you'd see just a simple or a single fixed support at the bottom. Now, the shear only wall won't work in its current state, and you can see that by, if you click on the validation icon or validate icon, you can see that it's flagging an error in the validation. If I expand the tree for walls and expand the tree for shear only walls, it's referencing, by double clicking, this shear only wall over here. And if I hover over that, it says there that the shear wall is not surrounded by beams and columns. Now, the reason it says that is because the shear wall, while it can support the forces laterally, it can't actually support its own weight. So it does actually need some form of supporting members to support its own weight. Now, the way to correct that would be to model columns either side of the wall. I'll just use steel columns in this example over here. And also to model beams. If I click validate again, we can see that it's still displaying the error. The reason is we need to have a beam at the very top as well. So that there is just a demonstration to show that any shear on the wall does need to be surrounded by columns and beams. It doesn't actually need a beam at the bottom. As long as it's surrounded by members at the top and on either side, that should be okay. So I now have another example over here where we've modelled shear only walls. So all of the walls, if I just rotate from the front, so all of the walls just to the right of where the cursor currently is are all shear only walls, and these two walls here are shear walls. So these walls over here, you can just simply tell by the supports that are underneath the walls. What I've also done in this model is I've applied wind loads in the X direction, so that's in the X plus direction, and a wind load in the Y plus directions, just simply to kick the building in these directions. If I were to run the analysis for these two load cases, and the solver's finished solving. You have options to view the reactions. I'm just going to turn on first the vertical reactions. And you can see over here, you have reactions as you typically would in a shear wall. So I'll just look at the wind wires. These are going to be much greater. And you'd also see reactions under these columns. These reactions aren't only because these columns are taking the load from the walls. What these columns are also doing is they are also taking the push-pull loads from the walls. So what you are seeing is, even when looking at wind Y, what you are seeing is, because you've got the push-pull effect, you are seeing that you've got a positive load on one side and a negative load on the other, or a negative reaction. It's the same as it is really for a shear wall. Like I say, push-pull effects are also considered. If I go back into wind X, you can see the same again. You can see that the push-pull effects are also considered when looking at the wind in the X direction. To view the forces within the wall, or the shear forces acting on the wall, the way to do that would be under your 1D results. If you click on the drop down, so this is the same way you'd view the results as you would do for any other member, as you can click shear wall forces, and you can see the forces that are acting on the shear only walls. Zooming in, you can see the magnitude of the forces better, and you can also see the directions that they're acting in. What would also be helpful is turning on things like the horizontal reactions, and you can see the effects at the, I've turned on the FY reactions over here, and you can see what the reaction is for the shear wall within this support over here. So this horizontal reaction here is looking at the shear effect, or the shear effect that's happening within this wall, and the vertical reactions at the end, while they do consider the forces acting on the columns, they also consider the push-pull effects of the or the internal forces within the shear only wall too. What we can also do with the shear only walls is we can create a report to show the forces within the walls. So I'm going to click on Model Report. I'm going to create a new report style and call this Shear Only Wall Forces. And to find the shear only wall forces, the chapter can be found under Analysis, scrolling all the way down to the bottom, and here is the shear only wall forces. If I drag that onto the report structure, I'm then going to create a loading filter. I've created one previously called Wind Only, just to show that Wind Only includes the 2 wind load cases. If I click on OK, to include only the wind only forces, I'm going to keep the analysis type as analysis method as first order linear. Model filter, I'm not going to create a model filter as there aren't many walls in the model. If I click on OK, select that report style and click on Show Report, we can see the forces under the different load cases in all three shear only walls for all 3 stacks. Thank you for listening. We'll now take questions. Any questions which do require further research or a longer answer will be sent to you in an email after this webinar on a later date.